So this question is about the speed control, and we have now a shunt motor. We have which was example 4.2, and then we have discussed as in example 4.6 also, which was rotating at no load speed. Ia is equals to 6 ampere, and then at full load Ia is equals to 120 amperes. Now for a machine, we have a, for example, DC machine, and we want to control its speed. So for a shunt motor, this is the typical characteristics. We have a terminal voltage Vt, a current It is flowing from the DC source. It flows as If and as Ia. This is Rf, and this is Ra, and this is internally induced voltage Ea. So the voltage control for these types of machine, there is a very typical example where we have a speed here, okay, we can say, and we have torque speed characteristics, and this is a very important speed. For example, there a motor has a base speed, and we call it omega base. Base speed is actually the rated speed of a motor. That is its nameplate rating. It's called, for example, 1000 rpm. So what we can do is we can control the speed of motor from its base speed, from 0 rpm to its base speed, and also beyond its base speed. And there are two methods by which the speed of motor can be calculated. The first method is known as voltage control method, where the terminal voltage of the motor, if it is changed, it will change the speed of the motor. So for example, the rated voltage is 400 volts on the nameplate rating of the motor. So at 400 volts, the motor rotates at base speed. So what we can do is we can gradually change from 0 volt to gradually increase the voltage up to 400 volts. So as we slowly change the voltage, the speed of the motor will also change as we change this speed of the motor. The speed of the motor will gradually change. So increasing the voltage in a ramp, we can maintain the torque constant for the machine, and we can vary the speed of the motor. And we know that P convert is torque into speed. So the speed of the motor will gradually change from 0, but torque will be fixed. So if we look at the power that is consumed at this time, it will be like this straight line, increasing up to the rated power that the machine can withdraw. And when it will reach at this point base speed, this will, so the speed of the motor from 0 up to the base speed is the maximum rated speed written on the nameplate. We perform this through VT control method. The next method, if we want our motor to have a speed more than its base speed, for example 1000 rpm motor, we want it to rotate at 3000 rpm or 2000 rpm. This can only be done when we will now the motor is already rotating at its maximum power. We cannot make motor consume more power. It will go beyond its rated capability. So if we want to increase the speed, we have to decrease the torque of the machine to keep the power constant. So the motor that will be running at higher speed will now be producing lower torque. So this will be achieved like this, and so the torque will decrease, and the power will remain. Red is for power. This control can be achieved, which is through IF control, field current control. If we decrease, for example, if we will increase the value, and if we decrease the value of IF, this will increase this current. So these are the method to control the speed of motor, and this is actually done through variable frequency drives, not variable frequency drive, DC drives. DC drives are used for DC motors very commonly in industry to maintain the torque speed curve of the motors. So this was the basic theory behind this. And now let's look at the question. What the question is saying? The question is saying that we have this DC machine. Determine the armature reaction. Determine if of the shunt field. So the question is, previously I was looking at the other example. This is the question. A variable speed drive system uses a DC motor. So a variable speed drive system, we have a variable speed drive here with our motor. This is a DC drive, and the torque and power profiles are as shown here in the diagram. The drive speed is varied from 0 to 1500 rpm. So the base speed we have is N base is 1500 rpm, and we are varying the voltage from 0 to 500 volts with the field current that will be maintained as constant. So the field current is constant in the machine, and we are varying the terminal voltage. So we are basically performing VT control for the machine. Determine the motor armature current if the torque is held constant at 300 Newton meters up to the base speed. So the base speed is 1500 rpm, and the terminal voltage is actually equals to 500 volts. That is actually approximately equals to EA. Now how we can do this is, we know that EA equals to K phi omega. So K phi can be, we can write K phi equals to EA over omega, and this will actually becomes becomes 500 volts divided by omega is actually 1500 into 2 pi. We have converted this into radians. So the value of K phi will be equals to 3.1831. What we are targeting is, we want to calculate the armature current, and we know that armature current is actually equals to torque K phi IA. So we have to calculate IA, and IA is actually equals to torque into K phi IA. So K phi IA we have calculated from the induced voltage. If we substitute this, and torque, it has told us that it will keep it constant at 300 Newton meters. The torque here, this red one, is kept constant as the voltage is changed. So when the voltage reaches up to the 500 volts, so it wants to know at that time what will be the armature current. So the value of IA will be 94.2477 amperes. This is how we have calculated this. Now in the part C, it says that the speed beyond the base speed is obtained by field weakening. Field weakening effect is known as we increase the value of our base resistor, RF, the field current becomes low, and when the field current becomes low, the motor speed increases. So this is known as field weakening effect also. While the armature voltage is held constant, now the voltage is at 500 volts and we are going beyond our base speed, that is we are into field current control mode. Determine the torque available at the speed of 3000 rpm. Now if the armature current is held constant at this value, now we are not changing V terminal, we are not changing the armature current, that is 94.247. So what is changing is actually the torque will be changing. The power will remain same, but the torque will gradually change. So for the part B, if we change the color of the pen, for the part B, if we look at our question, the N is actually equals to 3000 rpm, and again Vt, that is EAE, equals to approximately 500 volts. Now what they are torque available. Now again we need to calculate the torque. We know that K phi IA. So IA, we know it is remained constant, but this K phi factor will not be the same. So how can we calculate this new factor? This is actually EA equals to K phi omega. So now the new speed, the omega n, the new speed is actually EA over omega n. EA is again 500 volts and omega n is now 3000, and we have actually performed the field weakening effect there. That is why we have to again calculate the flux and this machine constant. And so this will be 2 pi into 60, and this factor's value will become 1.5916. Now when we put this value here, so the torque will become, IA is, as it is said, it has remained constant, so the torque will be 150 Newton meters. So the torque has decreased from 300 as we go to 150 Newton meters. This is due to the field weakening effect that is carried out here. And lastly, it also asks us determine the torque speed at this if the armature current is held constant at this value. So this is how we can calculate our value. Another way to calculate this torque is also, I will briefly tell you that in the machine we have the converted power. So the converted power is actually, we know that EA IA equals to torque induced into the speed, so the new speed. So the omega n will be EA IA and the torque induced, the new torque that will be induced will be EA IA divided by omega n. So EA IA is actually 500 into 94.247, and this will be the new speed converted to radians per second. So the new torque will again becomes 50 Newton meters. It's same as this. Both are the same theory. So this was related to a variable speed control of the motor. I hope it helps. Thank you.